Hello there. Let's talk about chemical equilibrium today. First, look at the books on the table. It's a static equilibrium, what is used in physics. But in chemistry, we're going to talk about the chemical equilibrium. What's a chemical equilibrium? Let's take a glass of water and there's water liquid there and it's going to evaporate, right? So it makes the gaseous water molecule by evaporation. So that's also we can consider as forward reaction. So it goes away, right? So we will lose all the water by it will be gone, right? But if you close it, that's called the closed system. So we need a closed system in order to have an equilibrium. So dynamic equilibrium. So what do you have? Water condensation back to the liquid water. That's the reverse reaction or the backward reaction. That's how you get a chemical dynamic equilibrium. Right. We will go to the next step. Yes, here we have, let's consider what's happening with the time, because time is needed to reach the equilibrium. Okay, to achieve the equilibrium, time is needed. So let's see how do we get there to the equilibrium. So if I have a graph like that, so against time and let's say the molarity of whatever the material, and in this case, let's say water vapor, right? So actually the liquid water amount is keep losing by evaporation. So the rate is going to be slowing down, right? But the vapor amount is going to increase and increase and increase by condensation. And that's why it's going up, the red one, the reverse one, right? We also write it like this way: water liquid, balance between water gas, that's the equilibrium, plus the delta H, because heat should be taken, heat should be given into the liquid water. Yes, heat should be given into the liquid water to vaporize it, right? We're going to have to warm it, right? So that's what we should be doing. Okay, so let's see. Yes, that's good. So it's back. It just, there's a glitch. Okay, so we're still good. So heat and water liquid together will give you water gas, right? This one also we call, if you go backward, the red arrow shows delta H, the heat is lost. It's called the delta H minima. So the delta H minima I just consider as this kid, this girl, which is mini, right? Let's say. And look at the other side. And a liquid going to the gas is the forward reaction, the blue arrow. And that's, let's say, delta S is max. That means more chaos, more randomness, because liquid to gas, there's a lot of freedom, a lot of randomness. So that is increased. That's called the delta S max. Let's call this little boy is delta S maxi. So the mini and maxi riding this seesaw, right? And that is the dynamic chemical equilibrium. So that's what we see here. So delta H min and the delta S max should be opposing each other in order to have this equilibrium. It's like a seesaw riding. You need both of parties working against each other in order to go do the ride. Okay? All right. So another thing we need to understand this way. Let's take these three graphs: potential energy versus progress. Progress is amount of molecules and bonds and so on. So let's say there's a reaction. Potential energy is higher in the reactant and lower in the products, and it goes into the product through the activation energy, little hump there, right? And in this situation, let's say if it is going 100% to reactant to the product, it's like, burning fuel, explosion, something like that. The delta S maxi and the delta H mini is going into the same direction, which is products, and that's why it's completion 100%. That's spontaneous. Go to the very other end. So the reactants are lower here, products are higher. So what happens? It's a really hard climb to go, right? Riding from reactant to the product to go all the way there is a very high activation energy, and it's not supported, let's say chances are 0 to go there, right? It's something like, you know, making a gold rust, something like that, or something never going to happen, diamonds combustion, something like that, right? Just imagine. So the delta H max is stay in the reactants, and delta S max staying the reactants, delta H mini stay in the reaction. So therefore it's never going to happen. It's a non-spontaneous. You can actually do it though, that's a different story. So look at this one, the middle one, the reactants and products are in the middle range. So the delta S max and min actually going opposite direction, just like the seesaw. That's why we're going to see an equilibrium. So the left and right is not really important, it could be either way, but this graph and the opposing forces of delta S max and the delta H min is important for an chemical equilibrium, a dynamic equilibrium. Alrighty, let's look at an example. What's that? PCl5 going to PCl3 and Cl2. We started with a bunch of PCl5. It's losing. That's how the graph should look like for the molarity of the PCl5. Now PCl3 and Cl2 going to combine, come back. That's the backward in purple, and that's the backward reaction. The earlier we had the forward in green, right? So the forward is lowering, and the backward was increasing, and these two gonna meet each other, the same rates, right? So the same rates are, yes, against time like that, and the same rates are equal. That's why it's an equilibrium. So any of these points are equilibrium, right? Now let's look at this one. This one shows concentration against time, and the concentration of PCl5 is losing, and it's going to go into a plateau, and PCl3 and Cl2 going to increase, and it's also going to go into a plateau, but they are reactants and product concentrations are never going to be the same. They have a same ratio. So that's why we call the K equilibrium is product over reactants, and that ratio is the same. If it is not K equilibrium, we call it Q. So that comes later. Okay. And so that's about the PCl5, back and forth to PCl3 and Cl2. Right, so two different graphs, really important to understand this idea of the two graphs, how to explain. Now let's go to the next little thing, which is the mathy part, and that's the ice table stuff, right? So that's how we actually do the problem solving using the ice table. I call the rice table because ratio also important. So ratio in this case 1:1:1, right? And the initial change equilibrium, and molarity is the only one we're going to put there. Let's say 0.2 molar initially PCl3 and Cl2 nothing, and then lows minus x gets x and x, because we don't know how much. That's why it's a minus x, and we don't know how much we got. That's a plus x. That's how you do it. So ratio, we can keep it separate. It's needed, but we can keep it separate from the ice table, right? Okay, so this has a bit glitch again, right? But I think we can still write the equilibrium law, which is KEQ, sometimes we call KC. That is actually product concentrations over reactant concentrations, or KC is PCl3 Cl2 over PCl5. Right, the ratios are 1:1:1, so nothing changes. This is the equilibrium law. The math connection, math formula is the one, right? So you can also plug in the molarities, x and x divided by 0.2 minus x. That's the equilibrium molarities. Plug into the product over reactants, right? So that's the formula. Now the questions could be, you're looking for Kc, you're looking for product concentration, looking for reactant concentration. So those are the questions. So you will be given two, and then we're going to have to work on an ice table to figure out what's missing, right? Okay, so let's take another one, another example. Calcium carbonate equilibrated with calcium oxide and CO2. Note there are two solids, calcium carbonate and calcium oxide. So if you do a rise table, the solids don't have a value. So nothing, nothing, and 1 for the CO2, let's say. That's for the ratios, right? And then the initially nothing, nothing, and then if let's say lose minus x, you get x and x, right? So Kc would be in this case product over reactants. Now the reactants were calcium carbonate solid, so we don't write the solid, that's just 1. So it would be just CO2 because that's the only gas or aqueous we have, right? So that's how the calcium carbonate equilibrium with the calcium oxide and CO2. And let's look at another example, right? Okay, now we can see actually there was a bit glitch here, right? Yes. Okay. So hydrogen and iodine equilibrium with 2 times of Hi, all gases. You can do a rise table, right? 1, 1, 2, and then 0.5, 0.5 you added, 0 at the beginning, minus x, 2x because of the coefficients, and then you can write the law. Kc is P over R, Hi divided by H2 and I2. Notice this 2, that's the ratio 2 goes as a power, right? The other ones are 1, 1, nothing to worry. Okay, now, so we can also put this on for a common any reaction like this way. That's the one you're going to see, AB giving you CD. The coefficients are simple A, simple B, simple C, simple D. You can write Kc is product over reactants. The products are C and D. Reactants are A and B. Then the powers are the blue CD, blue AB, right? That's how for any reaction you write it. So the problems, again, the same way. They can ask you, what's the Kc, what's the concentration of C, D, A, B, anything, right? So that's the use of ice table. I'll get you some more examples in the next video. Now, another important thing we call the LCP or Le Chatelier principle. To me, I simply say it's a Mother Nature fights back. So the system is happy and equilibrium, you disturb and the Mother Nature will fight back. So simply what it means, you do any changes to temperature, concentration or pressure to a equilibrium system which is closed, and it will try to undo the damage or the pressure you are adding by shifting left or shifting right by changing the equilibrium point, right? Yeah. And let's look at this example. This is ammonia production. So 3 hydrogen, nitrogen gives you 2 ammonia and 92 kilojoules are released exothermic. So delta S max C or max is in the reactant side because there are many gas molecules, more randomness. Delta H mini, the exothermic is in the right side. So that's a equilibrium 2 forces, right? So this is also the Habor method. So the Habor process is really important. We always want to get more products, right? In the 1950s, Fritz Habor came up with this great idea. He won the Nobel Prize for it, right? So what's the idea here? Let's say you increase the reactants and system will fight back by using the reactants, so you will get more products, right? You take away the products ammonia to clean your windows or something, and then the system will fight back to make more missing products. So we are happy, we get more products, right? That's the idea simply. So also you increase pressure. The system don't like increasing pressure. So it's going to fight back by making less molecules or less gas moles. So here you can see the Habor process happening. So in the upper part, warmer and equilibrium happens. The lower part, actually, it's cooler and the ammonia liquid is taken out from the system. That's how this Habor process system works. Okay, so the 450 Celsius heat is needed for the activation energy. We cannot cool it more than that. And also the pressure is actually 200 atm because higher pressure cannot be controlled.